So this, if we're faced with an integral like this, we might first think, well, I'm not going to integrate something times log very often. But if you notice, this technique applies when n equals 0 as well. And the only, what we're going to talk about is if f of x is not even. Now, if f of x were even and n equals 0, then we would use the normal technique and just say, well, it's even, so we can integrate from minus infinity to infinity and just half the value. So this is actually a very useful technique to evaluate integrals from 0 to infinity of functions which are not even. So the trick, and this is the first instance of something which happens when we consider more advanced types of integrals to do via the residue theorem. Rather than, at first sight, we would think that we would consider this contour integral. But if f has these properties, it's not even, there's no branch cuts, and there's no poles on the real axis as well, then if you did this, you wouldn't get very far. You would sort of get 0 equals 0. You wouldn't get anything useful. So it turns out that rather than try and evaluate this contour integral, we evaluate the one with log z raised to the power n plus 1 when we want to find the integral in. Okay, so we're going to now see how all this works. So first thing is, of course, we need to specify our contour. So that, okay, well, I'll get rid of this now. Is the usual one that we would expect. We're going to integrate from 0 to infinity, so normally we like to have the branch cuts along the values of x that we're integrating along. And I should add that f of x is of course allowed to have singularities along the negative real axis, just not along the positive real axis, for the time being anyway. Okay, so we have a contour which looks like this, and let's see what happens if we consider this integral. So as before, this is radius r, and we have this distance here we're going to call epsilon. So along here, we will get the integral, because we're integrating z along here is just x, so we're just integrating this with z replaced by x. We've of course got the integral in plus 1, which is not the integral we want. But what's going to happen is that this later term will, this term here will cancel out with the later term. So then we need to evaluate the integral around this loop here. So it's limit as r goes to infinity of f of r e to the I theta. So doing things in a sort of general way. N plus 1 r e to the I theta. We've got a factor of r. I coming out, and okay, that's all we have. Okay, so this is sort of difficult to do in a general way, but basically, how do we tell if this is going to go to 0? Well, basically, if we have, if we end up with, for example, let's just say that we end up with of order log r over r to the alpha, okay, whatever alpha is. How do we determine what happens with that? Well, the simplest way is just to think, well, really the rule is that if any r to any positive power will beat log r. But if you don't believe that, you can always write r equals e to the lambda and substitute that in and let lambda go to infinity. So then you have log r is equal to lambda, and on the bottom you've got r to the alpha then is equal to e to the lambda alpha. So yeah, no problem. Exponential always beats polynomial as lambda goes to infinity. So as long as alpha is positive, this will go to 0. So obviously it depends on what your f is. Then this crucial thing is the next step. So what happens in the next step? So when you integrate along this line here, then we've got z equals, let's write it as z equals x times e to the 2 pi. Because remember, the argument is going from 0 round to 2 pi. So if we write it like this, then we end up with the integral from infinity to 0. Then we've got, now remember this has no branch cuts, so nothing, we can just replace the z by x if there's no branch cuts. So the e to the I 2 pi just is 1 if there's no branch cuts, no problem with that. But then when we do this, we're going to have log of x e to the I 2 pi, which gives you log of x plus I 2 pi. And all of that is raised to the power n plus 1. And this is now dx. Then we also need to consider the integral around here. It's not so important, but basically it's the same idea as what happens here. We've got f e to the I theta log n plus 1 epsilon e to the I theta epsilon e to the I theta d theta. Again, you look at what's happening here and you get order log epsilon times something. So let's call it epsilon to the beta. Now, it's the same idea. If you want as epsilon goes to 0, sorry, this epsilon goes to 0, not infinity. As epsilon goes to 0, this will go to 0 if beta is positive. Again, we can show that if we let epsilon equal e to the minus lambda and let lambda go to infinity. Then we've got log epsilon is equal to minus lambda. And we've got epsilon to the beta is equal to e to the minus lambda beta. So when you multiply these two together, you can see, well, exponential beats polynomial. So as long as beta is positive, then this will go to 0. Okay, so the important bit is what happens here. So we can swap this to a minus sign and swap the limits. And what have we got? Well, we can expand this using binomial expansion. And you see the first term when you expand this binomial expansion will be precisely I n plus 1. But we've got a minus sign. So the first term in this expansion will cancel exactly this I n plus 1. And we'll end up with the I n plus 1 will cancel out. And we'll end up with minus I 2 pi times I naught. I should be a bit careful. So then, okay, if we, I should really, okay, I'll get rid of this. Log x plus I 2 pi to the n plus 1. Well, what's that equal to? The first term is log x to the n plus 1. Then you've got, just use your binomial expansion, you've got n plus 1 times log x to the n times this term, 2 pi I, and so on, plus, plus, etc. So when you expand all of that out. But basically, you will get, sorry, I wrote this wrong. This thing here will give you n plus 1 times in plus all the other terms you get by expanding this down to I0. So you've got plus, the last term would be, of course, I 2 pi to the n plus 1 times, so you've got a minus sign here, times I0. So you could then work out what in is if you've done your homework and worked out what these other ones, the in minus 1 down to I0 are, and all of this is going to equal 2 pi I times the sum of the residues. Okay, so this gets complicated if n is large, but if n is, for example, 0, it's very straightforward.